In this lecture, we will learn the concepts of amplitude modulation with a few examples. So first of all, modulation is the technique used to transmit low frequency baseband signal from sender to the receiver in a communication system. Amplitude modulation is a type of modulation in which the amplitude of carrier signal, which is a high frequency signal, is modulated by the modulating or the message signal. Two signals involved in amplitude modulation are message signal and carrier signal. Where message signal x m of t is given by a m cos of omega mt, and the carrier signal x c of t is given by ac cos of omega ct. In these signals, am is amplitude of message signal and omega m is angular frequency of message signal. Similarly, AC is the amplitude of carrier signal and omega c is frequency, the angular frequency of the carrier signal. The resulting amplitude modulated signal can be represented as xam of t and is given by xc of t, which is the carrier signal, plus xm of t multiplied by the carrier frequency, which is cos of omega ct. Expanding these values, we can get so here we take AC cos of omega ct is common from the both terms, and we get x m of t divided by AC plus 1. So this is the equation or the resulting signal of amplitude modulation. We name these equations equation 1 and equation 2. Further, we want to expand the equation number 2 as xam of t is equal to AC cos of omega ct into 1 plus am cos of omega mt divided by AC. And we call this equation number 3. The term AM by AC is known as modulation index and is represented by M. So, the equation number 3 will become XAM of T equal to AC cos of omega T into 1 plus M into cos of omega mt. Where M is modulation index. In amplitude modulation, the value of modulation index varies between 0 and 1. Zero modulation index represents that there is no message signal therefore there is no modulation. The modulation does not occur because the modulating signal does not exist, while the value of 1 represents 100% modulation. This also represents the ideal case, which is desired in amplitude modulation, or it is also the best case which is desired for the complete recovery of the transmitted signal. In this video, we will also discuss the waveforms of amplitude modulated signals with no modulation and with 100% modulation, and with an example where the value of M is between 0 and 1. For now, we will come back to our equation. We want to further expand this equation as and now we use our desired trigonometric identity, which will result in this term represents that there are three frequency components in this signal, which is omega c. The second frequency component here is omega c plus omega m, and the third frequency component is omega c minus omega m. This will help us draw the frequency spectrum of amplitude modulated waveform that we will see in our following example. we have the signal x m of t, which has an amplitude of am, and it varies between minus am and m on time scale. Similarly, we have a carrier signal. This amplitude varies between AC and minus AC. Now, this is the carrier signal which we represent with xc of t, and it is a high frequency signal, so it will be, as we know that the amplitude of this carrier signal will be modulated by this low frequency message signal. So now we will go into the graphical representation of the envelope that is formed. So here we mark AC. This point is then AC plus AM, and this point is AC minus AM. On the negative y-axis, similarly we have points. Here it is minus AC, here it is minus AC plus AM, and here we have minus AC minus AM. Now, as we have already stated that the amplitude of the high frequency carrier will be modulated by the amplitude of the message signal or the modulating signal. So here we want to draw the boundaries of the amplitude of modulated waveform. The amplitude of AM waveform, as we have stated, that it will be modulated by the amplitude of message signal. So here, as for our understanding, we have marked the boundaries of amplitude of this AM signal. The highest amplitude of amplitude modulated waveform will be equal to AC plus AM, and the lowest amplitude of this waveform that result after the amplitude modulation will be minus AC minus AM. The frequency of this signal will be same as that of the carrier frequency, or the frequency of the signal xc of t, which is represented by omega c radians per second. Now we draw the resulting signal. So this is how the amplitude modulated signal will look like. Now we can remove the boundaries that we had drawn for our own understanding, and we can see this is how our amplitude modulated signal will look like.